So I'm a physicist by training, but actually my area of interest and expertise is insulated windows for buildings, and specifically a technology called a vacuum insulated glazing. It's termed an emerging technology, but the technology actually goes back towards the 1800s when thermos flasks were invented. So it's a flat panel insulating design for a window, but unlike the traditional IGUs, which have a gas, what we do is we take the gas out, so it's an evacuated gap between the panes. Even though the technology has some age to it, our current innovations are trying to improve the manufacturing process, trying to innovate the components so that essentially the windows become super insulating compared to existing technologies, and in the near future, super cheap and easy to apply to most buildings. In terms of buildings, the traditional way to insulate the windows is our insulated glass units that are gas-filled, and we use air or argon to make sure that we can have the insulation levels we want. But in terms of those windows, what we have is a device that's quite thick. It can be anywhere between 10 to 20 millimeters in total thickness. So the vacuum glazing essentially tries to do two things. It essentially tries to lower the limit in terms of that thermal conductance and provide a super insulating window rather than the traditional insulating window, and then keep the thin profile. So the fact that we have an evacuated gap means that we have no dependence on the size of the gap. So if we're making an insulating window that's better than the traditional IGU, our width or total thickness of the window is only between 6 and 8 millimeters, but it is sometimes more than 50% better in performance. The performance we have with the vacuum glazing is similar to a triple IGU, which would normally have 3 pieces of glass, could be near 40 millimeters thick, so it's heavy, it's thick, it's hard to use. So a VIG with a thin profile, 6 to 8 millimeters, providing the same performance. That means fridge doors, heritage buildings where we install the windows from the inside and keep the old windows, but have this as an insulating layer. Existing residential where we don't want to change the frames because it is a single glass frame and we don't want to remove the nice wood frames, or we just don't want that expense. And any other actual building where the total cost of the renovation is going to be lower because the frames just don't need to be re-engineered for any of the thicker type insulating windows. So the profile helps with that. Skylights, roof windows, the weight is low relative to the performance as well. So in all of these cases, the VIG actually is, you could say, is a better product as a choice. So the production of a vacuum glazing is not the same exactly. It's about 80% the same as the existing technologies, but that last 20% is a little bit more complex. We have to be more careful because putting gas into a gap is relatively easy, but taking the gas out and making sure that we maintain that, what we call vacuum stability, that means that we have to be much more careful in the production process. It does produce a more durable product, but that complexity means time and cost is there for the process. Essentially, a vacuum glazing and an IGU are almost 90% the same. So essentially 95% of the products both have glass, float glass as their panels. The IGUs do have a spacer, they use silicone, butyl, materials like that. So we use a specific solder glass or glass frit or a metal solder for the edge. And we have these things we call little spacers or pillars that are also made out of a metal. In the end, the proportion of glass to other components is almost the same. And in terms of recycling or recyclability, silicone, butyl, aluminium, plastic that's in the others compared to, well, it's sort of on a qualitative point, they're about the same. So we would like it to be more recyclable, but I think that's one of the innovations for the future for both technologies, to be honest. Essentially, because we evacuate the gap, we can't have a seal that deteriorates over time. It essentially has to be, by definition, hermetic, which means no gases exchange, zero over its whole lifetime. So in terms of performance durability, ours is inherently, I would say, indefinite. But the durability side that's an issue is in terms of the construction and the way the mechanics of the two panels being bonded together works. If that design is not correct, then failure is likely to happen at some stage during a 30-year lifetime. But if we can design it correctly for the purpose, then we can design for those issues. And remember, those issues are complex for us. We have a unit that has atmospheric pressure, so it's a pre-stressed window. And then we have thermal loads, wind loads, baseballs being thrown at the window, people falling into them. So there's a lot of other possibilities. So we have to just be more careful in designing the window so that it suits the application. So, I mean, these are the innovations we need. So anybody doing work in the area of glass, future glass products and technologies, I encourage everybody to work hard and get involved. I mean, buildings are where we spend most of our time. Buildings in terms of energy use and embodiment, it surpasses all of the other sectors. So if we can improve our glass products in buildings, then inherently we're going to sort of make our lives easier. We're going to use less energy, we're going to have less embodiment and impact on the environment. And I think the vacuum glazing is that type of product. Once we innovate further so that the product is cheaper for everybody else to access, then we can see a product that's going to lower energy use and essentially lower our embodiment, better for the world.